Have you ever had this feeling, being in an empty room, yet feeling like someone is watching you? That's not a ghost story. It might be physics. Imagine, right here in this chair, at the same spatial coordinates, at the same moment, sitting another you. He's made of atoms, just like you. Except his atoms don't emit or reflect light. He might even be looking at his phone, scrolling through a mirror version of TikTok that you can't see. The distance between you is zero, but you can never touch, see, or hear each other. The only evidence of his existence is, you feel the chair is slightly heavier. That's gravity. This idea sounds like the wildest delusion in science fiction, but it precisely explains one of the biggest crises in modern cosmology. 85% of the universe's mass is missing, and we've just obtained the most crucial clue for 2026. We may have been looking in the wrong direction all along. Welcome to the Mirror Universe. This story begins in 1933. Swiss astronomer Fritz Zwicky, a hot-tempered but insightful genius, discovered something extremely illogical while observing the Coma cluster. Every galaxy in the cluster was rotating around its center at an incredible speed. Zwicky calculated the total mass of all visible galaxies, stars, gas, dust, everything. Then he calculated how much gravity would be needed to bind these rapidly rotating galaxies together. The result was astonishing. The visible mass provided only 1/400th of the required gravity. In other words, the cluster should have long since scattered into the vastness of space. But it hadn't. Zwicky concluded that there must be some kind of dark matter there, invisible but extremely heavy. His paper, after its publication, was almost universally ignored, because invisible matter sounded too much like the medieval concept of ether. 40 years later, a female astronomer named Vera Rubin brought this question back to the forefront of the scientific community. While studying the rotation speed of individual galaxies, she discovered an even more outrageous fact. According to Kepler's laws, stars on the outer edges of a galaxy should rotate slower than those on the inner edges, just as Neptune rotates much slower than Mercury in our solar system. But Rubin's measurements showed that the outer stars rotated almost as fast as those on the inner edges. You either have to abandon the law of universal gravitation or acknowledge that a massive, invisible mass halo surrounds the galaxy. This mass halo has a mass 5 to 10 times that of visible stars. Rubin's persistent observations transformed dark matter from an astronomical joke into the elephant in the room. By the early 21st century, a combined conclusion from multiple telescopes was that 85% of the total mass energy of the universe is dark matter. The atoms, molecules, you, me, Earth, and all the stars we are familiar with account for only 15%. So for the past 40 years, physicists around the world have been doing one thing: guessing what dark matter is. The most mainstream hypothesis is called WIMP, weakly interacting massive particles. The name is quite descriptive, heavy and shy. WIMPs only participate in two forces, gravity and the weak nuclear force. They are uncharged, do not participate in electromagnetic forces, so they neither emit nor reflect light. They do not participate in the strong nuclear force, so they don't stick to atomic nuclei. Theoretically, trillions of WIMPs pass through your body every second, and you feel nothing because their probability is so low. It might not even collide with an atomic nucleus in the entire age of the universe. To capture this specter, humanity has built the most expensive traps. We bury detectors 1.4 kilometers underground, using entire mountains to block cosmic ray interference. In Gran Sasso, Italy, the Sanford Underground Laboratory in the United States, and the Jinping Underground Laboratory in China, we have tons, even tens of tons, of high-purity liquid xenon or germanium crystals. We are waiting for a minuscule collision, a WIMP hitting an atomic nucleus and emitting a faint light. This type of experiment is called direct detection. Another group is taking the production route. Using the Large Hadron Collider, they shatter protons at near-light speed, attempting to create dark matter particles from the energy. If WIMPs exist, the energy after the collision would disappear into the unseen dark matter particles, manifesting as a loss of transverse momentum. The result? 30 years have passed, $5 billion invested, the careers of thousands of physicists. Zero signal. The Large Hadron Collider didn't find WIMPs. XENONNT didn't find WIMPs. Even the theorists who first proposed the WIMP hypothesis have begun quietly revising their resumes. Dark matter remains invisible, but what's even more terrifying is that it's starting to seem deliberately hiding from us. This brings us to 2026, a completely revolutionary discovery. In 2026, NASA's Nancy Grace Roman Space Telescope sent back its first batch of scientific data. Unlike Hubble, Roman was designed for a wide field of view. A single image can cover an area the size of a full moon, yet its resolution is equally astonishing. One of its main tasks is to map the three-dimensional distribution of dark matter in the universe. How? Through the gravitational lensing effect. Although dark matter doesn't emit light, it has mass. Mass bends spacetime, and bent spacetime bends light. By measuring g the minute distortions in the shapes of hundreds of millions of galaxies, astronomers could deduce where, how much, and how dark matter accumulates. This was a golden opportunity to confirm the WIMP theory, which predicts dark matter should be cold and clump-like, forming numerous small-scale dark matter halos. But what Roman saw? Smooth. Extremely smooth on a large scale. No large clumps as expected. This means dark matter doesn't behave like a bunch of randomly flying heavy particles. It behaves like a fluid. More importantly, Roman discovered previously unseen dark matter ripples around several galaxy clusters. These ripples, spanning hundreds of thousands of light years, were regularly arranged, as if some kind of structure was self-organizing within the dark matter. This structure couldn't have been formed by the random distribution of particles. It could only be the gravitational traces of larger-scale objects, such as dark galaxies or dark clusters. This discovery forces us to make a huge shift, from searching for tiny hidden particles to searching for massive hidden structures. Dark matter isn't a homogeneous soup. It might be a complete, invisible universe. Okay, now I must introduce you to a model that has quietly existed in theoretical physics for decades, but has always been considered too crazy: the mirror matter theory. The starting point of this theory is very simple. Nature may not have been a one-time event. In the very first instant of the Big Bang, the laws of physics may not have been born in one form, but in two forms. Imagine this scenario. In 10 to the power of minus 36 seconds, the universe underwent inflation and then cooled. In our visible sector, symmetry breaking gave rise to the electromagnetic force, the weak force, and the strong force, ultimately forming hydrogen atoms, stars, and you. But simultaneously, in the same space-time, in another sector, the same symmetry breaking occurs in a different way. It produces mirror electromagnetism, a force that doesn't interact with photons in our world. The physical constants in this mirror sector might be almost identical to ours, but with one crucial difference. Mirror photons don't interact with our electrical charges. What does this mean? It means that the mirror world can have a complete periodic table: mirror protons, mirror electrons, mirror hydrogen, mirror oxygen, mirror carbon. They can combine through mirror electromagnetism to form mirror molecules, mirror planets, mirror stars, and even mirror life. So, how do these mirror stars shine? No, they don't emit light that we can see. They emit mirror light. If we had a mirror eye, we could see that universe as bright as day. But to our eyes, they are completely dark. Their only leak is in their quality. This is why our Milky Way galaxy hasn't fallen apart. It's not spinning alone. There's an exact mirror galaxy, occupying the same region of space, pulling our galaxy along from the other side with its immense mass. The extra gravity we feel doesn't come from some mysterious particle soup, but from a twin we can never see. Why can gravity penetrate? Because gravity isn't a force, it's the geometry of space-time itself. If the visible universe and the mirror universe share the same physical space-time, that is, they're not in two different bubbles, but overlap on the same coordinate system, then the space-time curvature, i.e. gravity, they produce will superimpose. You can think of gravity as a universal language. Visible matter speaks it, and mirror matter speaks it too, with the exact same syntax. Electromagnetism and the strong nuclear force, on the other hand, are like dialects, completely incomprehensible to each other. Now let me give you a concrete image that will keep you up at night. Right at the center of our solar system, there might exist a mirror sun. It's as massive as our sun, or even larger. It's burning mirror hydrogen on the other side, emitting a huge mirror light. Our planets constantly feel the tiny gravitational disturbances from this unseen sun. But when astronomers point their telescopes in that direction, they see only a vast, cold void. Within that void lies a gravitational source 1,000 times larger than Jupiter. If you still think this is just theorists' wild guesses, let's talk about how to verify it. The discovery of gravitational waves has given us a key. When two mirror black holes merge, they release strong gravitational waves. These waves will penetrate our sector without hindrance. Currently, the black hole merger events heard by LIGO are at frequencies ranging from tens to hundreds of hertz. But the structures of mirror worlds may be larger, and their mergers will produce even lower frequencies, millihertz or even microhertz. This is precisely the target that the future space-based gravitational wave observatory, LISA, aims to detect. If LISA hears a perfect binary black hole waveform in an absolutely empty region of the sky, and that region appears blank to any electromagnetic telescope, then we have found the giant behind that wall. Every time humanity looks up at the stars, we think we have reached the edge of understanding. Copernicus removed us from the center. Darwin connected us to animals. Freud made us realize that we are not the masters of our own consciousness. And the mirror theory of dark matter offers the latest and most unsettling downgrade. We are not the only real entity in the universe. We might just be the brighter half of a binary star system. Right next to us, in the same room, evolution may have been going on for 13.8 billion years, giving rise to unseen civilizations. They might have had scientific revolutions, built telescopes, and wondered why the stars appear to be missing 85% of their mass. They might also be proposing the bright matter hypothesis and searching for those strange, luminous particles. If there truly is a mirror image of you in a mirror civilization, don't worry, he won't steal your chair. His chair is also made of mirror atoms, and the two of you can completely pass through each other while sitting simultaneously. The only strange thing is, the two of you combined would weigh twice as much as one person. The data from 2026 only lifts the curtain on the story. In the next decade, LISA will launch, the next generation of underground detectors will be activated, and China's OLI Primordial Gravitational Wave Project will search for the gestation of the splitting of the two universes at the time of the Big Bang. We will no longer ask what is dark matter, but rather what is the other universe like. Perhaps the final answer is, we are not alone. We just can't see each other. Doesn't this idea seem mind-blowing yet a little unsettling? If a mirror universe truly exists, what question would you most like to ask that other you? Tell me in the comments. Perhaps your question will be carried to the other side of the universe by gravitational waves and seen by that other you? Of course, he can't like it, nor can he see your reply. But you can like this video on behalf of your mirror brother. In this way, you've made a great contribution to communication between the two universes. Next time, we'll discuss an even more terrifying topic. If mirror life truly exists in the mirror universe, how would they communicate with us? Would it be war or a way we've never imagined?